Okay, good. Yeah, I hope everyone had a great lunch and all the demos and all the cool toys there. So yeah, thanks, Aaron and Maury, for that. And yeah, so I guess what I'm gonna I don't know if you want to briefly look at the afternoon session. You know, the first one, right, that I'm opening is for learning for autonomy. And then I guess we'll have the closing reception in the evening. Yeah, so when it comes to autonomy, I do think learning is a central piece of that, right? So the question is, how do we learn at scale, and how do we learn different kinds of complex processes that underlie many of the environments in which these systems operate. So I'll focus more on the machine learning techniques in the talk, as well as in the end tie them together to what you saw in the demo, for instance, the fan array, and that involves turbulence, right? And we have to think about flights under extreme turbulence. So how do we use machine learning to understand these complex phenomena of turbulence and do that in real time and potentially be aware, right? What we call being aware of the flow and aware of turbulence to quickly deal with it. And we see that in the natural world. Birds, fish, fly or swim under extreme turbulence. And our artificial systems are far from that. And what Maury is doing is bringing those principles from the biological realm into these autonomous systems, right? And what I'm looking at is how we can use principles in machine learning to learn phenomena like turbulence with high fidelity. And this is where I'll talk about neural operators as a framework in machine learning to learn fluid dynamics, to learn all kinds of phenomena like maybe deformable material properties, could be, of course, weather patterns, multi-phase flow systems, all kinds of different physical phenomena that we can learn. And once we learn this, how do we add control and bring that to an autonomous system? And to give you an example of how it is so infeasible to bring current traditional computational fluid dynamics or CFD tools to use them in, say, drones or other systems to predict turbulence, this chart just gives you an idea. Because, for instance, the biggest source in climate models and other models with turbulence is modeling these Navier-Stokes systems. How do clouds evolve under turbulence that's relevant for climate models? And here my colleague Tapio Schneider has these estimates that you need to go to extremely fine resolution to resolve these vortices and predict turbulence effectively. And in this calculation, if you want to do this for the entire planet, right, you have to go down to a resolution of about 100 meters, and that requires about 100 billion times more computing than what we have today, even with the biggest supercomputers. And so this is just to kind of give you an idea that trying to solve CFD with current numerical solvers is extremely expensive, right? And that's why what we call DNS, the direct numerical simulation, is almost never used in practice in any of the systems of interest. But we would ultimately like the fidelity of those systems because that's how we can deal with extreme turbulence. So that's the challenge, that's the moonshot. So what can machine learning do? Machine learning can overcome some of the limitations of numerical solvers by learning features from data and potentially learning better bases than what we use in a numerical solver, right? So in a numerical solver, you could use a pseudo-spectral solver, so that solves in the Fourier domain, or you pick some other basis. On the other hand, with machine learning, we learn that from data. So it's what we call adaptive basis learning, and that can potentially transform it to a latent space where resolving these fine vortices and these difficult turbulence phenomena become simpler. And the other benefit is these solvers are iterative, so they require a lot of iterations to converge. And potentially with machine learning, with a learned basis, we can make it much faster, right? Potentially with just a few layers as a forward pass in a neural architecture, we can get to very fast answers. And so that's what machine learning can do with learned basis, but also it sits on top of all the hardware and software advances we've seen in deep learning. We've seen accelerated computing being very effective, and we can parallelize these neural architectures effectively, run them at lower precision, so gets that better hardware efficiency than what we see typically in numerical solvers that are run on CPUs, right, that are run on legacy code. So you're also getting the benefits of the latest hardware and software in addition to a better learned feature representation. So that's the promise that machine learning has in terms of accelerating these different simulations for fluid dynamics and other domains. And so that's what we've seen with what we call neural operators, which I'll get into in a minute. But what it shows is this ability to predict different kinds. This is from a Navier-Stokes equation. And what you can do is train at a lower resolution and be able to predict at a higher resolution. So we take low resolution data, in this case 64 by 64 and certain points in time, and we do that over a certain number of trajectories. So different initial conditions for the Navier-Stokes equation. And so once it's trained, you don't just limit to the resolution that is prescribed in the training data. You can go and ask for a prediction on a completely different resolution, right, at a higher resolution. And what you see here in the spectral plot, because in the spectral domain, we can ask, how accurately is it capturing at higher resolutions? It's extrapolating to higher resolutions than what was seen in training data. And so this is the energy over different frequencies or wave numbers here. And this side of it shows what were the wave numbers seen during training. So that's limited by the resolution of the training data. And this is now asking for extrapolation or super resolution. What is the prediction of energy at different frequencies beyond the resolution of training data? And you can see here that the ground truth, that is this dotted line, is quite close to the predictions made by our method called the Fourier neural operator, where we learn this from data of limited resolution and can also predict further. On the other hand, if you take a standard neural network, in this example, the red line is the UNet, and then on top of it, add a standard interpolation. So you can always take a neural network outputting at the resolution of the training data and just do interpolation like bilinear interpolation or something that's standard, right? And you try to do that, and now you see that it's highly distorted. So which means it's not able to effectively predict at a resolution that is higher than the training data. And so in effect, what it's not learning well is what we call the underlying operator. Because when you write down fluid dynamics, that's an equation that can be discretized at any resolution, right? So that means it has a spectrum that's infinite, like you can keep going to finer and finer scales. And ideally, we want a surrogate model, a model that claims to solve this fluid dynamics equation, to have a good correspondence to the ground truth, no matter what the resolution is. So that's what would be the ideal case, because then it's a faithful solution to this underlying Navier-Stokes equation. And what we can do is, with our method, be much more faithful in capturing the finer scales than what we see with a standard neural network and adding interpolation on top. So effectively, what our method is doing is also trying to predict what would happen at a higher resolution, even when that information is not available. And I'll tell you in a minute how that happens. But before that, I want to add that we can further refine our method. It doesn't need to be only dependent on data. So if you look at language models, if you look at image models, it's purely data-driven, right? So you have data that is available and no constraints, no other information. On the other hand, when we think about Navier-Stokes equation, we have the actual equation at hand. And so what we do is impose that as a loss function in addition to the data we have. And in fact, we can impose the loss function from the PDE at a higher resolution because that does not need data. You can impose it at higher and higher resolution. So this way, we can make our output the solution that is given by our model under the physics-informed setting to be very accurate. And in fact, you can see this lying on top of the dotted line, which is the ground truth. So what the message here is, by combining data and physics constraints, in this example, the physics constraints are the equations themselves. And by combining this together, we can get very high fidelity solvers that are as good or even sometimes better than what numerical methods can do. And so that's the benefit we get with the machine learning method that is not only purely data-driven, but also can incorporate the physics. And so what we've done with Maury's group here is to ask, can we learn this kind of turbulence information directly from observations? In this example, it's the laser. I'm not sure why that part of the video is not playing, but it's, there's a cylinder and there's water flow, and with laser we can capture the vortices and observe the turbulence. And this is work led by Peter. I'm not sure if he's in the audience, but yeah. So what we see is the ability to track the evolution of these vortices in real time. So do this very fast. In fact, if I recall, thousands or tens of thousands of times faster than what numerical methods can do, and learn that even from noisy experimental data. So you don't need to just rely on simulations. You can directly learn from data. And we're also doing that as online learning as well, where in this work, again, that is led by Peter in Maury's group, we can do reinforcement learning and learn how to stabilize this wing under extreme turbulence. And our model, which is coincidentally called the Falcon, is it starts, I think it stands for Fourier domain-based learning, where we can do a model-based reinforcement learning, and the inductive bias of the Fourier domain helps stabilize well, and do it with much fewer samples. In fact, this translates to a few minutes in a wind tunnel to learn to stabilize, and do it much better than standard PID controllers, which do not have a good model of turbulence, and much fewer samples than model-free reinforcement learning, because by getting a good inductive bias and learning a model of turbulence, we can be much more effective in stabilizing it with much fewer samples. And of course, you saw the fan array, right? We have the potential to test all these methods as we develop in real-world conditions, in extreme turbulence, and do that under different kinds of wind conditions. So we've also been scaling up. I'm not sure why it rendered poorly here, but we've been scaling up to industrial scale, three-dimensional car aerodynamics here. This is like called the Ahmed bodies, the standard industry scale models used to determine turbulence, and we can now develop models now that are very fast, about 1,000 times faster than, or tens of thousands of times faster. So many other frameworks like material deformation we can do, weather models. Our weather model is now running in ECMWF side by side the traditional weather model. So you can go today and look at what our model is predicting. And it is much faster than what traditional models can do, but in fact, even more accurate in predicting one of the recent hurricanes, and that appeared in a Washington Post article. And that speed up can help with extreme weather. Again, the spherical geometry, the domain constraints is important. Other examples of multi-phase, such as the carbon capture and storage, where how does carbon dioxide interact with water underground and helping with predicting the pressure buildup and how the carbon dioxide gas plume migrates. So I'll stop here. There is many other examples of such simulation we can do in different domains. In terms of control, we've also been working in nuclear fusion and how to learn the disruption and then use effective control mechanisms. And we can do a lot of inverse problems as well. So you can ask, can I do a design optimization given the understanding of fluid dynamics? And that, I think, is very much open. We're thinking about better design of drones, propellers, with the use of that. In this example, it was a medical device called catheter where we improved with the use of these tools. So I'll stop here, and thank you.
Okay, great. So my name is Georgia. I'm a new faculty here. I joined this January, so 9-10 months. Before coming to Caltech, I was a research scientist at Meta, but I've been working for over 10 years on this problem that's called computer vision, which is basically building systems that can see like all of us can see, which is easy for us. We're built with that thanks to evolution, but machines are not. So how do we do that? And not only that, but we are in this exciting era in AI and machine learning because we now have these new tools that are called large models. I'm sure that you've all seen them. They're models that learn from vast amounts of data, and they're able to achieve generalization that we've never seen before. You've all played with ChatGPT, I believe, where you can ask it things like, write a song about Caltech's CAS seminar in the style of Bob Dylan, and it effortlessly gives you a song about today's event and makes it rhyme and so forth. Definitely Bob Dylan has not written a song like this, and yet the model is able to do this. And even more recently, there have been new capabilities that have emerged that we have seen, where you can upload an image of this flower and say, can you tell me the species? And ChatGPT will respond and say, this is leptospermum. I have no idea what it is, but apparently it's correct. And this is a very difficult problem for a lot of us. I'm sure that none of us actually know what this is, because it belongs in the space of fine-grained visual categorization. Another case, you can upload an image sitting in a cafe in Paris and say, can you enumerate all the objects? And there's even typos in the command instruction. And the model is going to be able to enumerate everything that it sees in the image without really any difficulty. And so what these models are doing is that they are taking a vast amount of image and language text description pairs, actually in the order of billions, and they deploy a computational model that ingests this data. However, the capabilities of what these models do and how well they do in downstream tasks very much is dictated by the type of input that they see. Not all visual tasks can be solved by having purely an image and image-level descriptions. And one such example is grounding. So for example, if you ask how many cupcakes there are in this image, the model will respond with 9. It's 12, so it completely misses one column. Or if you ask it to make decisions about how the objects are laid out in 3D, which goes to 3D perception, the models are completely unable to do this. They're not only confused, but you can also have them respond differently based on the instruction. So not all visual tasks, and I would argue the most useful visual task will not be solved by just image and image-level descriptions. So this is what I work on. I work on visual perception beyond language descriptions, trying to augment these capabilities. And in particular, I've been working on localization and 3D perceptions, which are really difficult problems. And in localization, we've actually had tremendous, it's playing. So this is the progress that we have made and what we can achieve right now with state-of-the-art object localization systems, where here you see a scene that the model has never seen before, and it's able to tell you what objects those are. And 2D is kind of easy, or we've been working on it for a while, so we're seeing great results, but 3D is even harder. And here I'm showing you some of the models that my team has built on trying to localize objects in 3D. So you see a video. This is a person wearing an AR device working around a messy apartment, and the objects predicted in 3D. So this is a very difficult problem, and definitely a problem that will benefit from having larger 3D data sets that are hard to collect. And so we're trying, so this is a data set that we put out, which is a data set of thousands of diverse scenes of over 3 million object instances in 3D that we are open sourcing and hoping that the community can build on. And we're seeing a lot of people, including roboticists, use this data set to deploy real-time robots. We're also have collected a lot of assets, 3D assets of diverse geometry, shapes, and textures. This is a collaboration with Stability AI and our colleagues in Seattle. And of course, there's a lot of great things that you can do by also scaling up your models. And you can achieve this generalization that I was telling you that we are seeing with language in the case of 3D, where you can reconstruct from just purely one single input the shape of the objects. Important here is tools as well, and you need tools to do learning, and building these tools is important, and open sourcing these tools is also important, but I'm going to skip it because I want to actually go into the second part of this talk, which is towards unleashing the capabilities of these models for other modalities. So right now we're seeing images and language dominate, but actually large models can be used for other modalities that are everywhere in the world, like time series, which actually represent a variety of complex systems. And so with the Sabera student here at Caltech, we've been working towards a foundation model for time series, and this is Sabera right there. And we wanted to study this problem under a wide umbrella, wide perspective, tackling many tasks and many domains. So we took time series data from a variety of domains, spanning with a lot of focus on the sciences, so climate, earthquake, neuroscience, et cetera, and also studied a variety of tasks, difficult tasks that people care about in the time series domain, such as forecasting, which is predicting the future, classification, predicting events that occur purely from time series measurements, and also translation, which is predicting measurements of an unobserved sensor based on other sensor measurements. These are all quite challenging, and we wanted to see how much we can scale large models for this task in the domains. And the first question to address here is, what is the right data representation for time series? Now, these large models only are effective and capable if you actually represent data in a way that will allow them to draw these connections, these correlations in a long horizon. And time series have something that actually makes these models not work well, which is the fact that time series are continuous and they're noisy. So we need to think a little bit more in how we represent the data so that we can leverage these large models. And an innovation that we have, that we are presenting is this notion of tokenizing time. So we want to convert time from being a continuous data representation to a discrete one. And we do this with introducing a code book. But what this code book is not clear. Language is easy to tokenize because language consists of words, but time series are not. So we're actually learning this code book, so we are learning it end-to-end using an autoencoder that tries to extract the modalities, the juice of the time series patterns in a specific time horizon. And I'm not going to go into details because it gets into the weeds of things, but for example, I'm going to show you what this code book looks like, which are all the dominant patterns in all of these 3 different domains. This is now learned end-to-end, and these code books are able to reconstruct time series very accurately. So we convert a continuous time series to a discrete one with only a finite size of code books that are able to represent the time series very well. And now being able to do this, we can unleash these large models, these large transformer architectures for a variety of downstream tasks. And while doing so, we are able to beat state-of-the-art all previous time series methods that were on all of these tasks. And to note here that we're doing this with one approach and one model, while all of these other methods in these different tasks are very much tuned for the specific task at hand. But more importantly, we're able to show generalization, which was not achieved before. So we're able to train on, for example, in the neuroscience domain, we're training models on a set of patients and then deploying them on a different patient. In the case of earthquake, we're learning these models on seismic activity from one geographical split, let's say North California, and deploying it in Southern California, and are able to actually achieve as good performance as in domain. And here's the result. Here's a qualitative result. We're showing this task for earthquakes. So this is our zero-shot model. It sees the east, west, and north-south activity from the seismic sensor. These are real data. And this is data that the model was trained in Northern California. And from these two inputs, it's able to predict the envelope of the vertical activity, which was actually a very difficult task. And seismologists were actually they wanted to do this for a while. And hopefully this model is going to be useful. And so this is the first result towards building this foundation model for time series. And we are now working on extending it and also looking for feedback if you have any and data or tasks that you think that we should be incorporating into this model. And I think I'm right on time, and thank you.
Our next speaker is Nico Christianson. He's going to be talking about robust machine learning algorithms for efficient grid operation.
Hi, I'm Nico Christianson. I'm a grad student in Adam Weirman's group. And I'm going to be briefly talking about robust machine learning algorithms for grid operation. So machine learning and AI achieve state-of-the-art performance in a lot of applications, from game playing to data center operation and self-driving cars. But there's one major problem when deploying to high-impact problem domains, and that's that machine learning doesn't come with worst-case guarantees. So there are lots of examples where adversarial attacks can cause classifiers to mispredict, and this is also a problem in high-impact domains like self-driving cars. But this is an issue if we want to deploy machine learning for decision-making in power grid, because if we make mistakes about dispatch operations, that can lead to large-scale blackouts. So in our research, we're largely focused on the question of, can we give AI and machine learning worst-case guarantees? So AI and machine learning occupy this regime where they achieve good performance on average, but have poor safety and robustness. And traditional algorithms, on the other hand, have good safety or robustness guarantees, but might suffer worse performance on average. So our research is in developing learning augmented algorithms where we try to get the best of both worlds in performance and guarantees. So the main idea of algorithmic results in this direction is we want to design algorithms that can switch between machine learning and standard approaches, or make mixtures of decisions there. And so the algorithmic paradigm is that basically if the machine learning is doing well, you want to follow it more closely. And if your traditional algorithms are doing well, you want to follow it more closely. So a motif here is if we want our algorithm to stay in these convex regions, our algorithm, by staying closer to the machine learning, is able to achieve smaller overall trajectory length compared to the traditional approach because it follows the machine learning more closely. And so this is sort of an intuitive idea, but the key challenge is theoretical in that you need to figure out how closely you stay to the machine learning. And we provide theoretical performance bounds showing that we can achieve performance close to the machine learning while also having worst-case performance guarantees, even if the machine learning models are adversarial. And we think a lot about applications to energy systems. And so one of our applications is in partnership with Beyond Limits, where we're thinking about cogeneration operation, where we have combined cycle generators producing electricity and steam. These are non-convex system models with a lot of variable renewable generation. And so it's a hard dispatch problem to figure out optimal dispatch decisions. And while machine learning is fast and efficient and can take into account future forecasts, it lacks worst-case guarantees on feasibility and safety. And so in our experiments, we can see that machine learning outperforms traditional algorithms as well as optimal algorithms in terms of runtime. And here in this plot, you can see that the machine learning in blue, when there's distribution shift, it suffers in performance. And the traditional algorithm achieves the same performance under distribution shift. And our approaches of learning augmented algorithms really bridge the gap between these two regimes when there's distribution shift. So we get the best of both worlds. And in ongoing work, we're looking at how to incorporate novel uncertainty quantification methods into machine learning augmented decision making. We're thinking about other types of performance metrics in addition to costs, such as constraint satisfaction, fairness, and we're also thinking about energy and sustainability problems more broadly. That's all. Thanks.
So now the program will continue with Mickey Liu, who's going to talk about optimal surface pressure sensor parameters for lift prediction of airfoil up to gust. Thank you.
All right. Hello, everybody. My name is Mickey. I'm in Professor Bay's group, and today I'll be talking about optimal. Oh, sorry, forgot this. And today I'll be talking about optimal surface pressure sensor placement for lift prediction of an airfoil subject to gust. So in other words, we're trying to find the optimal sensor placement on an airfoil. And why do you want to do that? So our final goal here is to mitigate lift fluctuations in gusty conditions for UAVs, which can be achieved. Sorry, there's a missing bullet point here, but which can be achieved with onboard active control. And controlling the lift fluctuations is relevant because of the small size of UAVs and that turbulent flows can be very detrimental to their flight. But it's a difficult task because of the nonlinearity and the chaotic nature of turbulence. But it can certainly be done if you just look at how nature navigates turbulent conditions. So for example, in birds, we see that we see albatross flying steadily in turbulent winds over the ocean, and we can also see fish using what's called the neural mast, which is shown as bright spots in this picture here, as sensors to detect disturbances in the water and act on it. But before we can do anything about control, we first want to investigate how we can optimally place the surface pressure sensors in order to correctly predict lift using the sensor informations. And this is our current objective. So the question we want to ask is where and how many sensors to place on the surface of the airfoil. And the answer to this question is often answered by heuristics in similar studies. For example, this is from Peter's work, and you can see the flow sensors here are usually placed at the leading edge of the airfoil in experimental studies. And however, there exist data-driven methods. That we can exploit to try to find the optimal sensor locations. And now we want to evaluate the different methods to find the best one. So the methodology for finding the best method for the optimal sensor placement can be split into three parts. First, we want to simulate an airfoil in turbulent conditions to collect the pressure and lift data. Here we're using a well-resolved LES simulation to solve for the flow through a NACA 12 airfoil at a radius number of 10 to the 4th with varying angles of attack and different inflow conditions. Then we want to identify the optimal sensor locations using data-driven methods, including POD, the proper orthogonal decomposition, and the Bayesian experimental design, which computes the entropy as a measure of the information gained at each location of the airfoil. And the last one, we have the attribution algorithm, which is a method that can identify which features are contributing to a model's output. So after we have the sensor locations, we use deep learning to predict the lift with them and compare the errors to find the best method. Okay, so these are the 5 cases that we simulated using the well-resolved LES simulation. Some of the cases are for training, and while the rest are only for testing. So here we mimic the gusty inflow conditions by placing a cylinder directly upstream of the airfoil. Here, hence the name cylinder in the case titles. There are also some cases called none, which are just cases with uniform inflow and no disturbance. Here we have these numbers here indicating the angles of attack of the airfoil. Right, so these are the results for the 10 most optimal sensors found using the different methods. Here we can see that the attribution method is integrated with the integrated gradient algorithm, which computes the attribution values. And then I guess the main takeaway from this slide is that different methods will give us very different optimal configurations of sensors on the airfoil. So now the question is, to determine which configuration is better, we can use models such as LSTM, which is what we did here. And by comparing the lift prediction errors, we can see that the attribution method with integrated gradient algorithm implemented give us the smallest prediction error, which means that this method is what we think the best method for finding the optimal sensor location is. So just to summarize, we found a good method for finding the optimal sensor placement on airfoil for lift prediction by going through these 3 steps. And in the future, we want to use reinforcement learning to mitigate lift fluctuations using the pressure sensors that we just identified. Thank you.
Hello, my name is Houman Owhadi. I'm an applied mathematician, and I will be presenting a project that has been funded by Beyond Limits via GUST. The focus of this project was on automating the design and discovery of models or of optimal models. Those are the people that have been funded at Caltech through this project. And this project has been a highly collaborative one, so we have been developing our technologies in collaboration with Beyond Limits, and we have been transferring some of these technologies to Beyond Limits. It has also led to a collaboration with Sandia National Lab and JPL. Now, this project had 2 main components. One focused on uncertainty quantification, and Pau will be presenting that part. And another one focused on developing a framework for automating model design and discovery through a generalization of Gaussian process regression from approximating input-output functions to completing computational graphs. The idea behind this generalization is that most problems in computational sciences and engineering can be framed and solved as approximating unknown functions and variables indexed by the nodes and edges of a computational graph whose structure represents their functional dependencies. And they can all be solved in a similar manner by replacing unknown functions by Gaussian processes and computing their map or empirical bias estimator given available data. The resulting computational graph completion framework is interpretable, and it comes with simple and transparent guarantees, both theoretical and computational, inherited from the guarantees of kernel methods. Now, I don't have the time to show you what this framework is, but I will refer to a poster shown by Yasamin after this talk. Now, I would just say that this framework is currently being transferred to Beyond Limits, and the motivation for developing it is that of reducing the complexity of solving most computational sciences and engineering problems to that of drawing a diagram. And the ultimate goal is to achieve a paradigm shift that has been achieved through the automation of calculus. An illustration of this point is that if I were to ask you to obtain the square root of 200 years ago, this is something that you will have done by hand, but if I ask you the same question today, you will just use your pocket calculator. And you will not think about the underlying technicalities. We are now at the stage where we can do the same thing with most problems in computational sciences and engineering. Most of these problems have technicalities that can be fully automated and encapsulated through essentially the drawing and completion of a diagram. I will stop here.
And for the uncertainty quantification part, we're focused on problems where safety is important, and so we want to use uncertainty quantification as a way to guarantee. So in these kinds of applications, we need uncertainty quantification that's both certifiable and well-calibrated. So we need a set of algorithms that are transparent about the assumptions that they make, and they are also precisely adjustable to the desired level of coverage. Because if we have an uncertainty quantification system that undercovers, we're actually incurring unnecessary risk, And if we have a system that overcovers, we incur the economic cost of having to prepare against extra circumstances that were not needed. And so with that in mind, we look at optimization problems that will result in intervals with frequentist guarantees. So we're trying to find intervals that are as small as possible, that have finite samples guarantees, and that contain a quantity of interest of the true parameter with a certain probability 1 minus alpha. With us, the practitioner, being able to change alpha. And this is a stronger notion of Bayesian credible intervals, meaning that it makes less assumptions and also makes it harder to devise algorithms that satisfy this. So we present a new optimization-based approach to this problem, which reinterprets previous methods and disproves a long-standing conjecture from 1965 and comes with an algorithm for constraint inverse problems with large generality. And just to end, here's a particular problem, and here's the result of our algorithm. We see on the left like the coverage at the desired level, 1 minus alpha, where previous approaches like overcover, the method proposed by the conjecture undercover, and we actually prove that. And our method, like, it's very close to the correct coverage and also very close to this oracle, which is like a best case scenario, while also being short in length of the interval.